Yes, David. Good morning. So I'm going to revisit the analysis of algorithms. Before that, what is an ADT? It is the abstract data type. So before defining the abstract data types, let us consider the different view of system-defined data types. We all know that by default, we have int, float, all these are primitive data types which support basic operations like addition, subtraction. So the system provides the implementation for the primitive data type, how an integer is defined, how a float is defined, etc. So for a user-defined data type, we also need to define operations. So the implementation of these operations can be done when we want to actually use them. That means in general, user-defined data types are defined along with their operations. And to simplify the process of solving problems, we combine the data structure with their operations and we call them as abstract data type. So this abstract data type, as I mentioned, has two parts to it. Okay. So the first part is the declaration of data, and the other part is the declaration of operations. So these are the two parts of an ADT, an abstract data type. So commonly used ADTs, what do they contain? They contain our common stack list, whatever we have seen in this course, um, like linked lists, stacks, queues, priority queues, binary trees, the dictionaries, hash tables, graphs, and many others. Now, for example, let's take stack, which uses last in first out mechanism while storing the data in data structure. The last element inserted into the stack is the first element that's get deleted. This is something which we know. So if you take stack as an example, right, it follows last in first out, right? So we're going to look at what are the common operations we do in a stack. Create the stack, then we do pushing the element onto the stack, removing the topmost element, which we call it as pop, right? And finding the current, what is the current top element, reading the top value, right? And also finding the total number of elements in the stack. So these are the maximum operations we do in the stack, right? So while defining the ADT, you define these declaration of operations. You don't have to worry about the implementation details. They come into picture only when we want to use them. So, so in this basic stack, we will define these as the operations. And they come into picture, implementation details are completely ignored. And you can have a different kind of ADT for different applications. Some might be for a very specialized specific task, etc. So we might have a very different ADT for them, etc. Required for them. Maybe we might have to use them on a different level. So there we might have a very different kind of an ADT, etc. So that is something we can define. But normally common ADTs are common operations. Right. Now we know what is an algorithm. It's a procedure. Now let's go back and revisit what is the analysis of the algorithm. Okay. The goal of the analysis of the algorithm okay, so we are going to go into analysis of algorithms. So this is what, remember, this is what we started this course with. Okay, that time you might have a generic view, but now when you go back to that, you will understand. After learning all the data structures, you go back to them, you get a complete understanding. So the goal of the analysis is to compare algorithms and or solutions in terms of running time and space, usually space required. So when we say running time, it is time complexity. And when we say space or memory, it is space complexity. So mainly we look at running time. So we compare algorithms in terms of running time, but we can also look at compare algorithms based on other factors like memory, development efforts, etc. So we will concentrate only on the running time analysis in this course. So the process of determining how much processing time is required by the algorithm and how the processing time increases as the size of the problem increases. So time, how much it increases based on input size, right? N. So if this increases, the time also obviously should increase. So, but how this increases, right? Whether linearly, quadratically, or polynomially. So that is what we are going to decide. So input size is basically the reference, the number of elements in the input, and depending on the problem type, we will have different input size, right? So number of elements, size of an array is an input size. Polynomial degree, number of elements in a matrix, number of inputs in a binary representation of an input, number of vertices and edges in the graph. So these are all the input size. So based on this input size, how the processing time or the running time of an algorithm increases, that is what we are going to measure in analysis of an algorithm. So now how do we compare? How do we compare algorithms? First, we compare the execution time. So not a good, so I told you what are the problems with the execution time, right? You have to first implement it, then you have to then do it. So it is not, and every computer might have a different requirement, right? So that's not a good measure, right? Number of statements or how lengthy the program is, can that be a measure? No. Sometimes simple statements, if you have 100 statements, it will not take much time. And it also varies according to the individual programmer and the style. So what is the right way to measure the algorithm? How do you express the running time of an algorithm? So you measure it as a function. You create a function of n, f of n, which is a function based on the input size, function based on input size n, right? So function of the input size n, f of n, you express the running time of a given algorithm as a function. And you compare the different functions corresponding to the running time. So this comparison is independent of mission time, programming style, etc. So now it's not just we compare. The most important thing we do here is identifying the rate of growth. So what are we doing here? Identifying the rate of growth means the rate at which the running time increases as a function of input is called as rate of growth. Okay. So we are looking at a way, or we are looking at an option through which we can measure the how much the running time increases based on the input size n. So let us assume you want to shop, you want to buy a bicycle or a car. Okay. If your friend sees you there and asks what you are buying, then in general, you say you are buying a car. This is because the cost of the car is high compared to the cost of the bicycle, right? So basically the higher amount is what the total cost is what actually you mentioned. So say for example, I ask you how much time it will take for you to reach your office from your home. You will someday you might reach in 5 minutes, someday it might take you 15 minutes, but when someone asks you, you always tell the maximum time possible. So you'll say 15 to 20 minutes based on traffic, right? So we can represent the cost of the car and the cost of the bicycle, or the shortest time and the longest time, in terms of a function which gives us the upper order, higher order terms that are relatively significant for larger input sizes. And we will be able to calculate the individual cost of some functions. And we will be able to find the rate of growth. Okay. So if you remember, so we had a function like say n squared plus 2n plus 10. We approximated to n squared. If you remember, right? So we had something like n cube plus 2n squared plus 3n plus 40. Then we approximated to n cube. Right. So since n4 or n cube or n squared, whatever represents the highest rate of growth, we take that. Right. So how do you represent the relationship between different rate of growth? Right. How do you say that that there is a significant rate of growth? Right. So linear 1. Okay. Order of 1 is the smallest. Then n linear growth. Right? So even before n, we will have, so 1 log n, right? Or even log of log n, then log n, then 2 power log n, then n, then n log n, then n squared, then n cube, 2 power n polynomial, quadratic, cubic function, polynomial, right? So this is how it goes.
Ma'am, it is very small, ma'am.
Is it better now?
Ma'am, the text is very small.
Now?
Ma'am, can you zoom it?
Yeah. I've zoomed it now, 100% and 120% I've kept it.
Okay, ma'am.
Are you able to see it now? I mean, you can zoom it in your browser individually also. Are you not able to zoom in, zoom out? I've shared the white
Yes, ma'am.
page.
Yes, yes, yes. Now it
So
is
it,
clear,
no, even
clearly
if
visible.
I reduce it, you should be individually able to zoom it, is it?
Yeah, ma'am. Now I'm able to zoom it.
Okay, fine. Okay. So this is the rate of growth. So the highest growth or the is polynomial exponential growth. right? So it starts with a constant, then logarithmic functions, then linear functions, linear logarithmic, quadratic, cubic, and exponential, right? So how do you analyze the algorithm? To analyze the given algorithm, we need to know which inputs the algorithm takes less time and with which inputs the algorithm takes longer time, right? So we have already discussed how to represent the algorithm in form of an expression. So now, in general, the first case, the best case is when you can get it in the smallest time. And the worst case is when it takes the maximum time. So we need some kind of a syntax and forms asymptotic, forms the base for the asymptotic analysis and notation. So there are three types of analysis we take into consideration. That is the best case, the worst case, and the average case. Okay. So in the worst case, you define the input for which the algorithm takes the longest time, slowest time to complete. Input is the one for which algorithm runs the slowest. In the best case, that defines the input for which the algorithm takes the least time and completes in the fastest time, right? And average case is a prediction, provides a prediction about the running time of the algorithm. It runs the algorithm many times using many different inputs that come from some distribution like normal distributions, etc., which generates these inputs and computes the total running time and taking out an average. That is, it adds the total running time done individually and divide by the number of trials, right? So if you look at that, you have, so the worst case gives the upper bound, the maximum time, right? And best case gives the lower bound. And the average time gives the average time gives the average. So the average will be greater than the lower bound and will be lesser than the upper bound. Okay. So for a given algorithm, we can represent the best, worst, and average cases in form of expressions, right? So let's take, this is the most important thing. We have done many examples in the very beginning. So let's say I have an algorithm which is defined by f of n is equal to n squared plus 500. Okay. So the time complexity will be around order of n squared. So this is the worst for the worst case. Okay. And then the same algorithm, we can say it takes this. This is the definition for the best case. Okay. So you can see this is order of n for the best case, right? So that's where comes the need for an asymptotic notation. So having the expressions for all three cases, we need to identify the upper and lower bounds. And to represent these upper and lower bounds, we need some kind of a notation. And that is where we are going to represent the algorithm in form of a function. So we start with big O notation. So this notation gives us the tight upper bound of a given function. So f of n, so the first big O. So f of n, this is the representation, is equal to big O of g of n, right? So g of n, the upper bound of f of n is provided by g of n. So if you have, say, f of n is equal to n4 plus n power 4 plus 100 n squared plus 50 n plus, say, 50. Okay. So what is the G of n here? How do you calculate? You calculate the largest value, right? So that is what we do for the worst case, the big O notation. So this will be n4. Okay. This means G of n gives the maximum rate of growth for f of n for larger values of n greater than n naught. Okay. Let us see the big O notation. Say when you say order of G of n, has to be defined in such a way it is an upper bound of f of n. So it should satisfy this particular, that is G of n should always be greater than f of n for all values of n greater than n naught, and c is a positive constant. So G of n is an asymptotic tight upper bound for the function. Our objective is give the smallest rate of growth possible, which is greater than or equal to the given algorithm's rate of growth. So that's why we discard the lower values of n. So because it becomes insignificant. That is why we ignore n squared, n, etc., and take the higher term, etc. Now, O order of G of n is a set of functions with smaller or the same growth of order of G of n. For example, if I say G of n is n4, this also includes n squared, n, etc. So because we are giving the upper bound. So when I give the upper bound, it doesn't mean that it has to be exactly equal to. So even of order of n, order of 1, order of n log n, which all is smaller, can be brought under big O of n. Okay. So when I say find, say let's do a small example. Say I give you an equation, find the upper bound of f of n is equal to 3n plus 8. Okay. Now, how will you calculate this? So how will you decide? So either you can add this as also, we usually add these constants 8 plus 3, 11. That's what we consider 11 n. And we say for all n greater than 11, that is n naught, the G of n value is equal to order of n or 11 n. Okay. So which means that 3n plus 8 will always be less than equal to 11 n. Okay. In some places, they just take 3n plus this also is counted as 1 n. So you will have 3n plus 8 less than or equal to 4n. So you can have this also. Okay, with C changing approximately based on, because C is something which is a constant and it can be any positive number, that's fine. So based on this, the C value and the N naught might change. Okay, so if I say, let me take a simple other example. Say I take f of n is equal to n squared plus 1. So I can make this as 2n squared, right? So I can say f n squared plus 1 will always be less than 2n squared. So C is equal to 2 here and n naught is equal to So that's how you calculate. So f of n is equal to, say, let's take a bigger term. Let's make it 2n cube minus n squared. Okay, so this is means we take 2n cube. So this is g of n. So what if this is f of n is a constant, say some 5, 10, like that. Then it will be g of n will be order of 1. That is, it will be 1. G of n will be just 1. Okay, order of 1. Order of g of n will be order of 1, and g of n will be. So there is no unique set of values for n naught and c when you're providing the asymptotic bound. So some of them consider just by adding it, or you can just take one value, etc. So that's completely fine. So even if it is, say I have, I'll take one more example to clarify. Okay, let's take 100 yen plus 5. Okay, so this is the function. Okay. Now, what are the possible, say there is no unique set of values as I mentioned. For this function, what are the different possible values of n naught and c? Okay. So one method we can follow is add these two, 100 plus 5. Okay. And we make it 105. So we say this 100 plus will be always 105 yen. Right. So here c becomes 105, n is equal to 1. Right? So this is also the right solution. Or 100 yen plus 5. So you just add these two terms and you just say 101 yen. Right here, c is equal to 101 and n naught is equal to. So this is also possible, right? So this way, you I mean you can take any option, but ultimately, if you see the complexity, it will not have a difference. So the rate of growth is what is important. So the rate of growth defines what is the tight upper bound in a big board notation. It is represented as order of g of n. So below n naught, we don't care about the rate of growth. We are not sure about the rate of growth. So n naught is the point from which we consider the rate of growth. Okay? It is the threshold for the given function. And c is any positive constant. So that is what we are saying. Now with this idea, let's go to the lower bound. So far we were been discussing the upper bound. So let's go to the lower bound. Okay, so omega, right? Omega notation is the lower big omega. So similar to the big O notation, this notation gives the tight lower bound of a given algorithm, and we represent it as f of n is equal to omega of g of n. Okay. This means at larger values of n, the tight lower bound of f of n is g of n. That's what we are meaning by this. So the omega notation this is such that it is defined such that for any f of n, there exists a positive constant c and n naught such that the whatever value you specify, right? C of G of n will always be less than or equal to f of n. So this is the lower bound. So the algorithm will not execute below that particular value. Okay, so this is what is the lower bound. It's asymptotic lower bound for the function f of n. Our objective here is to give the largest rate of growth, which is less than or equal to the algorithm's rate of growth. So how do you calculate this? So we have a function, say f of n is equal to 5n squared, right? So we have to have, we just usually drop the constants in a lower bound and we say 0 less than or equal to n squared less than or equal to 5n squared, right? So, or we can just take this as same, right? So C is equal to 5 and naught is equal to 1. Okay, so if you take another example, f of n is equal to, say, let's take 100n plus 5. Okay, you can just drop the other terms and you can just define 100 yen. Okay, or you can even add this 105 yen. Okay, so this will always be less than or equal to 100 yen plus. Or any positive n positive value, right? So if you take 2 of 2n, right? It will be omega of n. If you take n cube, it will be omega of n cube. That's how it is. So this is the lower bound. So you have a upper bound. The rate of growth will not go, the rate of growth of the algorithm will not go above this. Then you will have a lower bound. The rate of growth of the algorithm will not go below this, right? Now you have the third function, the theta notation, which gives both the upper bound and the lower bound of a given function. The average running time of an algorithm is always between the lower bound and upper bound of the function. So if a upper bound we go and lower bound omega give the same result, then the theta notation will also have the same rate of growth. Okay, so this is the, so let's take an example. Say for example, f of n is equal to 10n plus n is the expression. Its tight upper bound is order of n. Its lower bound is also order of n, right? So the rate of growth is order of n. The rate of growth in best case and the worst case are the same. As a result, the average case also will be same. If the rate of growth of order of big O and the lower bound are not the same, the rate of growth of average case, that is theta, also may not be the same. In that case, we need to consider all possible time complexity and take the average of this in between, right? So for example, in quicksort, if you remember, you have a best case. Remember, you can revisit quicksort example. So in quicksort, we have in a best case, it will do it in order of log n. And if the inputs are completely reverse, it will take the n squared, right? So how do you calculate the average case? You have to, all possible time complexities, you have to take and take a average out of it. Okay, so that is what about theta. So how do you define theta? It's between the upper bound and the lower bound. So for analysis, best case, worst case, and average, we try to give the upper bound and the lower bound and the average running time. From the above example, it should be very clear that for a given function, getting the upper bound and the lower bound, and that may not always be possible because we are discussing the best case, we might try to get the upper bound. If you're discussing the worst case, you might get etc. We try to get the upper bound, lower bound, and the average running time. We'll focus more on the upper bound because knowing the lower bound is we don't have much practical use. So that is why we always use big O notation more. And we use the theta notation if the upper bound and lower bound are the same. Okay. So now what exactly is this asymptotic analysis? We can easily understand that in every case for a given function, we are trying to find whether the g of n, how is the rate of growth which approximate the value of f of n at for higher values of n. So this means g of n is a curve which approximates the rate of growth f of n at higher values of n. So that is what we call it as an asymptotic analysis. And how do you perform that? You take a loop or any code, you identify the running time of the statements inside the loop, you multiply it by the number of iterations it performs, right? You derive out a function out of it and you calculate the time complexity it takes for each statement, right? Then you identify what is the running time it takes totally, right? So that's what we are doing. Let's take one small example. So let's take a loop for I is equal to 1, I less than equal to n, I plus plus. Okay. And m is equal to m plus 2. There is only one statement inside the loop. Okay. And now this statement, which will take constant time to execute C, right? And this loop, how many times it will run from 1 to n? So it run n times, right? So the total time taken by this algorithm is n into C, or we can say Cn, right? So it is order of n is the time complexity. Okay. Let's do a little complex example. Let's take a nested loop. This is the outer loop. Then we have an inner loop of j is equal to 1, j less than equal to n, j plus plus. K is equal to k plus 1. Okay, so this is what you have. Now this takes constant time, right? See, this loop executes n times. and this loop executes n times. So the total time this particular statement will run n times for every value of j, right? And for every value of I, it will run into n times all the values of j. So it will be f of n will be c into n, which is Pn squared, and it is complexity is order of n squared. Okay. So if it is a continuous statements, you have to just add the time complexity. If it is inside the loop, you have to multiply, right? So if this same example, we had a for loop, okay, and then say m is equal to m plus 2, and then we have another for loop which says k is equal to k plus 2. In this case, it will be n plus n, cn plus cn, it will be 2c n. This, it will be order of n, but it is a nested loop in the top case, so that is why you have it in the order of n squared. And if you have a if else statement, right? For example, say, let me take example. Say if length is equal to 0, then return false. Okay. Else say you have some statements. Say you have here you have a loop, for loop, for I is equal to 0, I less than equal to length I plus plus, right? So say I here have some if c is equal to some value, then the statement. So if I have something like this, then worst case, whichever part, if the if part takes longest time or the then part takes the longer time, whichever is larger, that is what you have to consider. Okay, so in this case, if you see, if part takes only one statement, so it's a constant, but the else part takes, say, this is 2n times, right? So this you have to ignore and you have to take the largest one. Okay, so you have to always take the larger part if in case of a if else statement, whichever takes the largest time only you have to take. And when do you get logarithmic complexity? An algorithm can run in order of log n time. If it takes a constant time to cut the problem size, it takes a, so you would have remember binary search, any tree based algorithm, heap based algorithm, all we have order of log n, right? So how that happens, say I have a loop for I is equal to 1, I less than equal to n, I instead of I is equal to I plus 1, say I is equal to I star 2. Okay. So now how initially if I is equal to 1, in the next iteration I will be 2. In the next iteration it will be 4. In the next iteration I will be 6. Right? So if it is I plus plus, it will be 1, 2, 3, 4, 5. Say n is equal to 10. Okay. And I is equal to 8. I is equal to 10. So this it achieves in say 5 iterations, but this it will take 10 iterations. So it reduces the running time by half. So the value of I is doubling every time, right? So the number of times to execute reduces by half. So so how do you calculate it? So let's say let's assume that k times the loop is running. Okay, let's assume that k times the loop is executing. what will happen at the kth step? This I is equal to I into 2, right? So 2 power k will be equal to n, right? So this is like 2 power 0. This is 2 power 1, 2 power 2, 2 power 3, 2 power 4, and 2 power 5, right? This is the last step. So in the last step, 2 power k. So say this loop runs k times. So in the last step, its value will be equal to n, which will come out of it. So 2 power k is the number of times the loop is executing. At the kth step, 2 power k will be equal to the value of n. Now at k plus 1, the step, what will happen? It will come out of the loop, right? So how do you, so now if you take a log on both sides of this, right, it will be k log 2. So it is a power equal to log n, right? So log 2 to the base log 2 is 1. So k is equal to log n. So the number of iterations of the loop, number of times the loop runs is log n times. So we assume base 2 here. Similarly, not only for I is equal to I into 2, even I is equal to I by 2. This in a binary search, it always divides, right? So that is also order of log n, right? So you have to remember a few properties of asymptotic notation. It is transitive, it is reflective, symmetry is also there. Okay? And you have to remember some logarithmic notations and properties. So log x to the y log x, right? Log n will be say log k power n can be written as log n to the power of k. Okay. Log ab can be written as log a plus log b. Okay, so some certain algorithms you have to remember. Okay, we'll take a quick break and come back. I will talk about more on this analysis. Okay, so let's continue. I'm going to write a function, okay, and I'm going to probably I will try to copy this function. Um, and see if copy is working. Yeah, it is working. Okay. So let's take this function. Okay. If you take this function, uh, you have a function, a void function, and you have some initialization, and you have two loops here or three loops here. Okay. So how many times does the outer loop executes? Outer loop executes, it starts with I is equal to n by 2 and it runs till n. So the outer loop executes n by 2 times. Right. And what about the middle loop? The middle loop will execute again, it starts with 1 and it runs, say it is j plus n by 2 less than equal to so it starts from j. J has to be n by j plus n by 2 equal to n. So n by 2, say if you have n is equal to say 10 and n by 2 is equal to 5. So every time you will be adding plus 5. So it will reach in the starting itself, you are adding plus 5 to it. So which means it's starting exactly from n by 2 only. Right. So you have to stop that. So this also executes n by 2 times. Right. And what about the inner loop? It starts from 1 and it runs till n, but k increments k into 2. So it is similar to our previous example. So this runs log n times. Okay. Now, what will be the total time complexity? So all this is nested loop. So the outer loop runs n by 2 times. Correct? Then we have into the n by 2, the middle loop, into log n. Okay. So it is 2n squared into log n. So maybe this 4 is also there. Okay. Maybe we can ignore this 2 and 4n squared by 4. Okay, so we can ignore this 4 and we can say it is order of n squared log n. So what is the time complexity? It is n squared log n. Okay, now I'm going to give you another example. Okay. So in this example, you can see we have n by 2 outer loop. It executes n by 2 times. Okay. The middle loop, it starts with j is, j is equal to 1, j, and it increments twice. So it runs log n times. And the inner loop, that also starts from n and it runs. So inner loop also executes log n times, right? So the total will be n into log n into log n. Okay. So it will be n log squared n. So this will be the time complexity of this. Okay. Okay, so now let's take another example. So in this loop, in this example, you can see uh, there is a if loop. So if this will take constant time, right? And then there is one outer loop. It executes outer loop executes n times, right? And inner loop executes how many times? It starts from j equal to 1, but there is a break. So it exactly executes only one time. So it is n into 1, 1 plus n into n. So it is order of n. Okay. So I want to talk about one important, as we saw asymptotic analysis, but along with asymptotic analysis, there is another important thing which I have talked about as it in the stack where I told it as a growable stack kind of a thing. So amortized analysis is the term. It refers to determine the time, average running time for a sequence of operations. It is different from average case analysis because amortized analysis doesn't make any assumption about the distribution of data values, right? Amortized analysis is a worst case analysis, but for a sequence of operations rather than for an individual operation. So if you want to understand the running time of certain techniques where worst case analysis provides a like it is pessimistic, right? So where the worst case operations, majority of the operations, it is cheap, but for some of the operations, it is expensive. Then if you take the worst case, it is always take the largest one and it will say everything will execute that, right? Expensive, if say, for example, always you reach your office from your home in 10 minutes, but say on a before a festival holiday or something, it took 30 minutes or 40 minutes, etc. Or if there is a rain, etc. So that's a rare event, right? So in that case, if you consider that rare event also, the worst case time complexity will be very high. So if you show that the expensive operations are particularly rare, then we can consider the worst, we can ignore them and we can change them to cheap operations and only take the bound for those cheap operations. We can ignore the rare operations. So the idea here is to assign an artificial cost to each operation in the sequence such that the total of artificial cost for the sequence of operation bounds the total real cost for that sequence. So this artificial cost is called as the amortized cost of an operation. So you have to have a correct understanding of the overall running time, but you have to also note that particular operations will take a longer time than the average running time. So when one event in a sequence affects the cost of all the other events, that one event can be expensive, right? So that is what is called as an amortized analysis. Okay. So recursive analysis we are not doing. We know what is a recursion. We know what is a Sorry, we know what is recursive function, etc. We know how it executes, but we are not taking into account the time complexity calculation. We will leave it that to other courses which you will learn in the future. Okay. I'm going to show you an example. Um, Okay, so remember the stack example. So let me revisit stacks. How do you check balancing of symbols, right? Um, so you take a stack, right? You take an operation. Uh, say we take something like A plus B star C plus D. Okay. So is this a valid? Is it balanced? Yes. Right. So if this is balanced, how do you identify this in the stack, right? If it is an operand, uh, you pop, and if it's a normal operator, you push. So that method is what um, you follow. So if the character red is not a symbol to be balanced, ignore it. If the character is an opening symbol, push it on the stack. If it is a closing symbol, then you empty it from the stack. If the symbol popped is not corresponding opening symbol, then you report it as an error. Right. So in this case, what will happen? First, you will push this symbol into the stack, then A plus B you will ignore, right? And when you encounter a closing symbol, you pop this. So this and this is matching, right? Then you proceed, then you insert this, again you pop that, should be matching, right? So in case if I have something like this, it's not closing, so I will insert this, Then when this comes, I will pop this out. Then I will again insert this. When this comes, I will pop this out. Then this will be remaining. Stack is not empty at the end. So it is time, is it not a valid expression? Now, what is the time complexity of this algorithm? You run from the starting of this expression to the end of this expression, right? So you run only once. So it is the number of elements in the expression, right? So it is order of n. The input size, the number of elements, you scan every input once. So it is order of n for a stack. Same concept you use for infix to postfix conversions also. You follow that expression, right? If it's an operand, you output it. If it's the parenthesis, you pop and output, push it out, right? And if you do this again using stack, you're scanning from left to right completely once, right? So that is why it is the stack based operations. That is where it is useful because you have the option to read the latest added element internally. So if you do the same thing with the linked list or any other implementations, it might take time. Okay, so with this, we complete the syllabus for the entire course. I will show you the handout. So we started with the array, stacks, queues. In queues, we saw the different types of queues, circular queues also. Then we saw list, single linked list, double linked list, etc. Then different sorting algorithms. Then when it came to trees, we saw trees, different types of trees, binary tree, binary search tree, ABL trees. Then we also saw heaps, min heap, max heap. And then we have hash tables, types of collisions, how do you prevent collisions, etc. Then analysis of algorithms. We also saw graphs, which is part of the recordings. So this is what is the entire syllabus for the exam, right? So next session, in the next session, we will do a quick revision of some important algorithms and other things which might be very important for your examination, right? So all of you please refer to the recorded lectures, refer to the PPTs uploaded for preparing for the examination. Do you have any questions?
No, ma'am.
Okay. Use the visualization tools for practice. There are many visualization tools. So if you want to understand how each data structure works, you please use the visualization tools because you might be given examples, inputs, and you might be asked to trace it down in the exam. So practice using the visualization tools. Okay. So next class, we will do a quick revision. I will close for now for today. Thank you.
Thank you, ma'am. Have a great day.